Hello, how's everyone doing? Let me just switch to full screen. Right. So last stream I was learning about control statements like if, switch, break, continue, and whatever. I also learned a lot about random numbers, but it was mostly reading. I didn't really do any programming in that section. This stream I'm going to start with chapter 9 and chapter 10 and maybe 11 also. We will see. Also, I switched to Windows Edge as my default browser. So I found this a little bit faster than Opera. So I'm going to be using this. Okay, anyways. And let me just check my. Shouldn't it show like building and stuff? Hold on. Okay, I need to update. STD, see out, and then let's just do testing. It's a 1:12 a.m. I think since it was already built before, it did not rebuild. I'm just checking how long this would take because my laptop is really slow. Anyways, let's just start reading the chapter. Introduction to testing your code. Hold on. Okay. If your program is entirely linear, has no conditional such as if statements or switch statements, takes no inputs, and produces the correct answer, then you're probably done. In this case, you already tested the entire program by running it and validating the output. But most likely, you have written a program you intend to run many times that uses loops and conditional logic and accepts user input of some kind. You have possibly written functions that may be reusable in other future programs. You may have experienced a bit of scope creep. Scope creep, where you added some new capabilities that were originally not planned for. Maybe you're even intending to distribute this program to other people. In this case, you really should be validating that your program works like you think it does under a variety of conditions. Just because your program worked for one set of inputs doesn't mean it's going to work for all cases. Software testing, also called software validation, is the process of determining whether or not the software actually works as expected. Before we talk about some practical ways to test your code, let's talk about why testing your program comprehensively is difficult. Consider this simple program. So this is a compare function. And we are doing compare xy. So you're inputting two numbers, comparing them, checking if it's greater or less than or equal. Assuming a 4-byte integer, explicitly testing this program with every possible combination of inputs would require that you run the program these many times. Clearly, that's not a feasible task. Every time we ask for user input or have a conditional in our code, we increase the number of possible ways our program can execute by some multiple factor. Your intuition should be telling you that you really shouldn't need to run the above program 18 quintillion times to ensure it works. You may reasonably conclude that if case 1 works for one pair of xy where x is greater than y, it should work for any pair of x and y. Given that, it becomes apparent that we really only need to run this program about 3 times to have a high degree of confidence it works as desired. Okay, testing your programs in small pieces. Consider an auto manufacturer that is building a custom concept car. Which of the following do you think they do? Which of the following do you think they do? Build or buy and test each car component individually before installing it. Once the component has been proven to work, integrate it into the car, retest it to make sure the integration works. At the end, test the whole car as a final validation that everything seems good. Or B, build a car out of all the components all in one go and then test the whole thing for the first time right at the end. It probably seems obvious that A is a better choice, and yet many programmers write code like option B. I mean, sometimes you might get lazy and you wouldn't want to test every case. In case B, if any of the car parts do not work as expected, the mechanic would have to diagnose the entire car to determine what was wrong. The issue could be anywhere. A symptom might have many causes. For example, is the car not starting due to a faulty spark, battery, a faulty spark plug, battery, fuel pump, or something else? In case A, the company tests as they go. Okay, I get the analogy. The above analogy holds true for programs as well. Though for some reason new programmers often don't realize it, you're better off writing small functions and then compiling and testing them immediately. That way, if you make a mistake, you will know it has to be a small amount of code that you changed since the last time you compiled or tested. That means fewer places to look. Testing a small part of your code in isolation to ensure that unit of code is correct is called unit testing. Each unit test is designed to ensure that a particular behavior of the unit is correct. Okay, if the program is short and accepts user input, trying a variety of user inputs might be sufficient. But as the program gets longer and longer, this becomes less sufficient, and there is more value in testing individual functions or classes before integrating them into the rest of the program. So, how can we test our codes in units? So, the informal way is this. As an example, for the following is lower value function, you might write the following code. Is lower vowel, switch case, AEIOU, return true or return false. If the results come back as 1 or 0, then you're good to go. You know your function works for some basic cases. Preserving your test. Although writing temporary tests is a quick and easy way to test some code, it doesn't account for the fact that at some point you may want to test that same code again later. Perhaps you modified a function to add a new capability and want to make sure you didn't break anything that was already working. For that reason, it can make more sense to preserve your tests so they can be run again in the future. For example, instead of erasing your temporary test code, you could move the test into a test vowel function. So is lower vowel, test vowel function. As you create more tests, you can simply add them to the test vowel function. Automating your test. One problem with the above test function is that it relies on you to manually verify the results when you run it. This requires you to remember what the expected answer was at worst and manually compare the actual results to the expected results. You can do better by writing a test function that contains both the test and the expected answers and compares them so we don't have to. So test verbal, if this false returns 1, if this is true return 2. Returns the number of tests that failed, or 0 if all tests pass. Wait, hold on. Returns the number of tests that failed. Wouldn't 2 mean that the second test failed and not that 2 tests were failed? You can call test vowel at any time to reprove that you haven't broken anything, and the test routine will do all the work for you, returning either an all good signal, return value 0, or the test number that didn't pass so you can investigate why it broke. This is particularly useful when going back or and modifying our code to ensure you haven't accidentally broken anything. For advanced readers, it's a better method is to use assert, which will cause the program to abort with an error message if any test fails. We don't have to create and handle test cases numbers this way. Okay, where did they use assert? Assert if define end debug. What's the full form of end debug? Test run with end debug defined. Asserts compiled out. Yeah, I don't know what's happening here. Because writing functions to exercise other function is so common and useful, there are entire frameworks called unit testing frameworks that are designed to help simplify the process of writing and maintaining and executing unit tests. Once each of your unit has been tested in isolation, they can be integrated into your program and retested to make sure they were integrated properly. This is called integration testing. Integration testing tends to be more complicated. For now, running your program a few times and spot checking the behavior of the integrated unit will suffice. Code coverage. The term code coverage is used to describe how much of the source code of the program is executed while testing. There are many different metrics used for code coverage. We'll cover a few of the more useful and popular ones. The term statement coverage refers to the percentage of the statements in your code that have been exercised by testing routines. Consider the following functions. Calling this function as foo10 will give a complete statement coverage for this function, as every statement in the function will execute. For our isLowerValue function, this function will require 2 calls to test all the statements, as there is no way to reach statement 2 and 3 in the same function call. Statement, oh, I see, statement 2 and 3. Branch coverage refers to the percentage of branches that have been executed. Each possible branch counted separately. An if statement has 2 branches, a branch that executes when the condition is true and a branch that executes when the condition is false. A switch statement can have many branches. The previous call to foo gave us 100% statement coverage and exercised the use case where x is more than 0. But that only gives us 50% of the branch coverage. We need to make one more call to foo01 to test the use case where the if statement does not execute. Wait. Code coverage is used to describe how much of the source code of a program is executed while testing. Okay, so there's, you go statement by statement or you go by branch. In the isLower function, 2 calls will be needed to give you 100% branch coverage. One to test the first case and the other to test the next case. Multiple cases that feed into the same body don't need to be tested separately. If one works, they all should. Now consider the following function. I guess this is one branch, this is one branch, and then this is a separate branch. 3 calls are needed to get 100% branch coverage here. Compare 1, 0 to test this, compare 0, 1 to test this, and compare 0, 0, 1, 1 to test this. Aim for 100% branch coverage. Loop coverage, informally called the 0, 1, 2 test, says that if you have a loop in your code, you should ensure it works properly when it iterates 0 time, 1 time, and 2 times. If it works correctly for the 2 iteration case, it should work correctly for all iterations greater than 2. So consider spam. So spam 0, spam 1, and spam 2. If spam 2 works, then spam n should work, where n is greater than 2. Testing different categories of input. When writing functions that accept parameters or when accepting user inputs, consider what happens with different categories of input. In this context, we are using the term category to mean a set of inputs that have similar characteristics. For example, if I wrote a function to reduce the square root of an integer, what values would it make sense to test with? You'll probably start with some value like 4, but it would be a good idea to test with 0 and a negative number. I guess one random positive number, one random negative number, and 0. Here are some basic guidelines for category testing. For integers, make sure you have considered how your function handles negative values, 0, and positive values. You should also check for overflow if that's relevant. For floating point numbers, make sure you have considered how your function handles value that have precision issues. Good double type values to test are 0.1 and 0 minus 0.1 to test numbers that are slightly larger than expected, and 0.7 and minus 0.7 to test numbers slightly smaller than expected. For strings, make sure you have considered how your function handles an empty string, an alphanumeric string, and string that have white spaces, and string that are all white spaces. If your function takes a pointer, don't forget to test null pointer as well. Here's common semantic errors. So semantic errors occur when you write code that does not do what you intend. The compiler generally will not catch semantic errors. Semantic errors can cause most of the same symptoms of undefined behavior, such as causing the program to produce the wrong result, causing erratic behavior, corrupting program data, causing program to crash, and so on. One of the most common types of semantic errors is a conditional logic error. A conditional logic error occurs when the programmer incorrectly quotes the logic of a conditional statement. So here they forgot to use greater than. Here they use greater than or equal to instead of greater than. So x is greater than 5. Okay. We covered infinite loops. Okay, they're talking about a case where it doesn't reach the condition. Even for for loop, I think it's the same issue. If it doesn't reach the condition, I mean, if the condition is never false, then the for loop will be running forever. An off by one error is an error that occurs when an off by one error is an error that occurs when a loop executes one too many times or one too few times. Here's an example. So count 1, count is less than 5, and plus plus count. The program intended for this code to print 1, 2, 3, 4, 5. However, the wrong rational operator was used. Isn't this conditional error? conditional logic error. So this is also off by one error. So incorrect operator precedence. From lesson 6.8, the following program makes an operator precedence mistake. I think the user is going to do is x greater than y and then not. However, this program does not first. Because not has a higher precedence than greater than, the conditional evaluates as if it was written as not x and then greater than y, which is what the programmer intended. Precision issues with floating point types. The following floating type variable doesn't have enough precision to store the entire number. Because of this lack of precision, the number is slightly rounded. In lesson 6.7, we talked about how using the operator equal equal and not equal can be problematic with floating point numbers due to small rounding errors. Okay, so 0.1 10 times is giving not this because of precision errors. Integer division. In the following example, we mean to do a floating point division, but because both operands are integers, we end up doing an integer division instead. So 5 divided by 3, I think this only returns the quotient, right? Accident and null statements, I think this is when they put a semicolon. Yeah, here. Not using compound statement when one is required. And these two should be in curly brackets. Using assignment instead of equality inside a conditional statement. So this will, y will be assigned to c and then c will be returned. That's the error. Forgetting to use the function called parameter when calling a function. Okay, that makes sense. The above represents a good sample of most common types of semantic errors new C++ programmers tend to make, but there are plenty more. Okay, 9.4. Detecting and handling errors. Most errors in a program don't occur as a result of inadvertently misusing language features. Rather, most errors occur due to a faulty assumption made by the programmer and or lack of proper error detection or handling. For example, if in a function designed to look up a grade for a student, you might assume the student being looked up will exist, all student name will be unique, the class uses letter grading instead of pass fail. What if any of these assumptions aren't true? If the programmer didn't anticipate these cases, the program will likely malfunction or crash when such cases arise. There are three key places where assumption error typically occur. When a function returns, the programmer may have assumed the call function was successful when it was not. When a program receives input, the programmer may have assumed that the input was in the correct format and semantically valid when it was not. When a function has been called, the programmer may have assumed the arguments would be semantically valid when they are not. Many new programmers write code and then only test the happy path, only the cases where there are no errors. But you should also be planning and testing your sad paths. We define defensive programming as the practice of trying to anticipate all the ways software can be misused. Function may fail for any number of reasons. The caller may have passed in an argument with an invalid value, or something may fail within the body of the function. For example, a function that opens a file for reading might fail if the file cannot be found. When this happens, you have quite a few options at your disposal. There's no best way to handle an error. It really depends on the nature of the problem and whether the program can be fixed or not. There are four general strategies that can be used. Handle the error within the function, pass the error back to the caller to be dealt with, halt the program, throw an exception. So handling the error, uh, if the error has occurred due to something outside of the program's control, the program can retry until success is achieved. For example, if the program requires internet connection and the user has lost their connection, the program may be able to display a warning and then use a loop to periodically recheck for internet connectivity. Alternatively, if the user has entered invalid input, the program can ask the user to try again. A loop until the user is successful. Okay, so they're manually handling the error by using if and else statements. However, if the calling function is expecting the call function to produce a return value or some useful side effects, then just ignoring the error may not be an option. Passing errors back to the caller. In many cases, the error can't be easily handled in the function that detects the error. For example, this y0, what should we do? We can't just skip the program logic because the function needs to return some value. We shouldn't ask the user to enter a new value for y because this is a calculation function, and introducing input routines into it may or may not be appropriate for the program calling this function. If a function has a void return type, it can be changed to return a bool that indicates success or failure. For example, void here, return false and return true. That way the caller can check the return value to see if the function failed for some reason. If the function returns a normal value, things are a little more complicated. In some cases, the full range of return values isn't used. In such cases, we can use a return value that wouldn't otherwise be possible to occur normally to indicate an error. For example, consider the following function. Double reciprocal, double E. The reciprocal of some number x is defined as 1 over x, and a number multiplied by its reciprocal equals 1. However, what happens if the user call this function has reciprocal 0.0? We get a divide by 0 error and the program crash. So clearly we should protect against this case. But this function must return a double value. So what value should we return? It turns out that this function will never produce 0.0 as a legitimate result. So we can return 0.0 to indicate an error case. A sentinel value is a value that has some special meaning in the context of a function or algorithm. Okay, so this is a sentinel value. If the error is so bad that the program could not continue to operate properly, it is called a non-recoverable error, or also called a fatal error. In such cases, the best thing to do is terminate the program. If your code is in main or a function called directly from main, the best thing to do is let main return a non-zero status code. However, if you're deep in some nested subfunction, it may be convenient or possible to propagate the error all the way back to main. In such cases, halt statements such as std exit 1 can be used. Because returning an error from a function back to the call is complicated, and many different ways to do so leads to inconsistency, C++ offers an entirely separate way to pass errors back to the caller: exceptions. The basic idea is that when an error occurs, the exception is thrown. If the current function does not catch the error, the caller of the function has a chance to throw the error. If the caller does not catch the error, the caller's caller has a chance to catch the error. The error progressively moves up to the call stack until it is either caught or handled. We will cover exception handling in chapter 27. when to use std cout versus cerr versus logging. By default, cout and cerr print text to the console. However, modern OSs provide a way to redirect output streams to files so that output can be captured for review or automated processing later. For this discussion, it is useful to differentiate two types of applications. Interactive are those that the user will interact with after running. Most standalone applications like games and music apps fall into this category. Non-interactive applications are applications that do not require user interactions. The output of these programs may be used as input for another application. Within non-interactive applications, there are two types: tools and services. Tools are non-interactive applications that are typically launched in order to produce some immediate result and then terminate after producing such a result. Example of this is Unix's script command, which is a utility that searches text for lines that match some pattern. Services are non-interactive applications that typically run silent in the background to perform some ongoing task. An example of this would be a virus scanner. So you have it. So you have interactive applications and wait, hold on. Non and in non-interactive applications, there are tools and services. Here's some rule of thumb. Use std cout for all conventional user-facing text. For an interactive program, use cout for normal user-facing error messages, like your input was invalid. Use cerr or a log file for status and diagnostic information. That may be helpful for diagnosing issue, but probably isn't interesting for normal users. This includes technical warning and errors. For non-interactive programs, use cerr. This allows errors to be displayed and passed separately from a normal output. For any application type that is transactional in nature, use a log file to produce a transactional log. There wasn't much programming this chapter. Also, I forgot to print, like when I was printing them, normally I have to open the answers so that I can read the answers when I'm on stream, but I forgot to do that this time. So I won't have access to the answers. Most programs that have a user interface of some kind need to handle user input. In the programs that you have been writing, you have been using stdcin to ask the user to enter text input. Because text input is so free form, it's very easy for the user to enter input that is not expected. As you write programs, you should always consider how users will misuse your programs. A well written program will anticipate how users will misuse it and either handle those cases gracefully or prevent them from happening. A program that handles error cases well is said to be robust. In this case, we will take a look specifically at ways the user can enter invalid text input via stdcin. Here's a simplified view of how the operator, would you call this extraction, I think, or insertion? First, leading white spaces is discarded from the input buffer. If the input buffer is now empty, the operator will wait for the user to enter more data. Operator then extracts as many consecutive characters as it can until it encounters either a new line or a character that is not valid for the variable being extracted to. The result of the extraction is as follows. If any characters were extracted in step 3 above, extraction is a success. If no characters could be extracted in step 3 above, extraction has failed. The object being extracted is assigned the value 0. Any future extractions will immediately fail until Cn is cleared. Validating input, the process of checking whether the input conforms to what the program is expecting is called input validation. There are three basic ways. Inline, prevent the user from typing invalid input in the first place, and post entry, let the user enter whatever they want into a string and then validate whether the string is correct. And 3, let the user enter whatever they want and let stdcn or operator try to extract and handle the error cases. Some graphical user interfaces and advanced text interfaces will let you validate input as the user enters it. Okay, let's see what they did here. Copy. Let's see. So double x get double, right? It's getting double. And then get operator. Oh, it's that exercise they were asking. So this gets a character. And then double again. Get operator. And then print result. Print the result. Okay. So they want to validate the input by checking if I actually typed the correct input. What happens if I type a letter? Okay, so they input 5, enter one of the following, and then they got input 7, and then the output is 35. So why do we have this error? Five plus 7 is 12. Okay, it's doing it correctly here. Okay, there's no error. They did times. But we ask the user to enter some number. What if they try to enter some other number? Let's see. L K. Second, we ask the user to enter one of the four possible symbols. What if they enter a character other than the one symbol we are expecting? I think that's easy to handle. We can just handle it in the switch case. You can generally separate input text errors into 4 pages. Input extraction succeeds, but the input is meaningless. Input extraction succeeds, but the user enters additional input. User extraction fails, and then user extraction succeeds. So let's look at error 1. Extraction succeeds, but the input is meaningless. So they input K over here. In this case, we ask the user to enter one of the 4 symbols, but they entered K. And then this would return this. That makes sense. The switch value fails, it will just skip the function. So in the end, it's going to do print result. So X 5 5 K 7. The solution here is simple. Do input validation. This usually consists of 3 steps. Check whether the user's input was what you are expecting. If so, return the value to the caller. If not, tell the user something went wrong and have them try again. So while true, stdc out. Or you can only go out of the while loop if it uses this return operator. Error 2, extraction succeeds but with extraneous input. Consider the following execution of the above program. What do you think happens next? And let's just try this. Wait, what happens if there's no space? So 5 and then times 7. This works. If I do 5 times 7, this does work. 5 times 7 is 35, but it doesn't ask for any other input. The program prints the right answer, but the formatting is all messed up. Let's take a closer look why. When you enter 5 times 7 as input, the input goes into the buffer. The instruction extraction operator extracts the variable 5 to variable extracts 5 to variable x. However, when the extraction leaving times 7 in the buffer, next the program prints enter one of the following plus minus star slash. When the extraction operator was called, it sees times 7 slash n waiting consequently. When asking the user to enter another decimal number, the 7 goes in the buffer, gets extracted without asking a name. Then the user never had an opportunity to see additional and hit enter cause Enter causing a new line. Wait, I'm feeling sleepy. Enter causing a new line. Hit enter causing a new line. The output prompts all run together on the same line. Although the above program works, the execution is messy. It would be better if an extraneous character entered were simply ignored. Fortunately, it's easy to ignore characters. Okay, so c dot ignore 100, clear up to 100 characters out of the buffer. Wait, to ignore everything up to and including next neoline character, we call std ignore numeric limit stream size. Okay, I don't really understand this part. Okay, this ignores 100 characters out of the buffer or until a new line character is removed. Wait, hold on. So get double cn. Let's see. I don't clearly understand because with 5 times 7 I did not input 100 characters, right? Or they are they just using it as an example? Because this line is quite long for what it does, it's handy to wrap it in a function, which we call in place of std cn ignore. So ignore line function. Why would you ignore here? Shouldn't you ignore before cn? In certain cases, it may be better to treat extraneous input as a failure case rather than just ignoring it. We can then ask the user to re-input their inputs. 5 times 7. Wait, I don't understand. What was that? So first 100 characters or a new line, right? Hold up. In certain cases, it may be better to treat extraneous input as a failure case. Here's a variation of get double and ask the user to re-enter their input if there is any extraneous input entered. So get double while true, enter a decimal. Now has unextracted input, ignore line and then continue. Um, this works, but I don't know why the other case did not work. C in end of file function returns true if the last input operator reached the end of the input stream. C in peek function allows us to peek at the next character in the input stream without extracting it. Okay, error case 3, extraction fails. Extraction fails when no input can be extracted to the specified variable. Now consider the following execution of our updated calculator program. Enter decimal number A. You shouldn't be surprised that the program doesn't perform as expected. But how it fails is interesting. Okay, let's try that. Whoops. Exited with code 0. This looks pretty similar to extraneous input case, but it's a little different. Let's take a closer look. When the user enters A, that character is placed in the buffer. The operator tries to extract A to variable X, which is of type double. Since A can't be converted to double, the operator can't do the extraction. Two things happen at this point. A is left in the buffer, stdcn goes into failure mode. Once in failure mode, feature request for input extraction will silently fall. Thus, in our calculator program, the output program still prints, but any requests for further extractions are ignored. This means that instead of waiting for us to enter an operation, the input prompt is skipped, and we get stuck in an infinite loop because there's no way to reach one of the invalid cases. Um, in order to get stdc in working properly again, we will need to typically do three things. Detect the prior extraction has failed, put cin back in normal operation mode, remove the input that caused the failure. So cn clear. So if cn fail, cn clear, then ignore lines. I forgot what clear does. Oh, does it reset it? You mean clear the settings? Because stdcn has a boolean conversion indicating whether the last input succeeded, it's more idiomatic to write the above function as this. Let's see. How much is left? I'm having a hard time reading. I think I might continue this next stream. Wait, hold on. While editing output, Hold on. Let me just do Control Shift V. Whoops. So 4 types. Input succeeds. Then this and this. And then for the first case, extraction succeeds, but input is meaningless. Okay, so put the user in the loop and ask them to try again. So this is for the first one. For the second one, extraction succeeds, but with extraneous input. What they used was C end of file and C and peak. What's the output of C and peak? But extraction succeeds, but the user enters additional input. Hold on, let me just copy this. Okay, there's no mouse click for Control Shift V. The std enter file function returns extraction to true if the last input operation, in this case x, reaches the end of the input stream. The std peak function allows us to peek at the next character in the input without extracting it. Does the peak return, like if there's no character after it? So what is this case again? For additional input. So if it's not the end of the file, so the input stream hasn't ended, and peek the next character. What is this output though? If that next oh, wait, these two are together, and then this is together. Okay, the structure confused me. So if it hasn't reached the end of the file, or if it um, if it hasn't reached the end of the file and the next character is not a new line, then just skip and just ignore line. But you already input it, right? So what's the point now? Hold on. Let's try this. So clear up to 100 characters out of the buffer or until a new line character is removed. Hold on. If I do get double, ignore the next 100 characters. Clear up to 100 characters out of the buffer or until a new line character is removed. So either 100 characters removed or new line removed. It's going to take time to load. Then case 3 extraction fails. Let's put a box around that. Extraction fails when no input can be extracted to a specified variable. Okay, let's see. Now let's test. Enter decimal, I enter 5. And then I do this. Then times 5. Okay, so it ignores all of this K, O, P, K and everything. So what happens if I do 54 and then some invalid? I'm guessing 5 goes into X, 4 goes into X, but the next one is an invalid character, so C in skips. And then, yeah, it works the way I expected it. Hold on. Should write this. This clears. Out of the buffer or until a new line character is removed. Oh, it's written here. Is there a way I can format a text? Let's see. Can I do this? Oh, but it changes the entire thing. You shouldn't be surprised that the program doesn't perform expected, but how it fails is interesting. Okay, so they input A, then input is invalid. And let's check this. So if I input, let's say P, it is invalid, but it's a valid character though. Or in their program, they put it inside a loop, right? They updated the function. So if I type P, so 0, P, and then they shouldn't they ask for another input? Or does it terminate? Why does it do this? Hold on, let me see. Is there a way to view the input buffer? I want to see the characters inside. Okay, so in their version, this is inside a loop, and the last line keeps printing until the program is closed. This looks pretty similar to the extraneous input case, but it's a little different. Let's take a closer look. When the user enters A, that character is placed on the buffer. The operator tries to extract A to variable X, which is of type double. Since A can't be converted to double, operator can't do the extraction. Two things happens at this point. A is left in the buffer and Cn goes into failure mode. Once in failure mode, future requests for input extractions will silently fail. Thus, in our calculator program, the output prompt still print, but any requests for further extractions are ignored. Oh, that's why. This I need to remember. This means that instead of waiting for us to enter in operation, the input prompt is skipped and we get stuck in an infinite loop because there is no way to reach the valid cases. In order to get C in working properly again, we typically need to do three things. Detect that a prior extraction has failed, put C in back into normal operation mode, remove the input that caused the failure. Wait, in their version, what is ignore line? Numeric limit stream size max. I don't understand what is numeric limit STD stream size. Um, okay, let's see what they do. So get double and then ignore line. I'll just input this. And then the loop thingy. Control C. Let's see. Switch operator is return operation. Wait, this is in the wrong function. Uh, let's see. Okay, so we have those two things. And then what did they do in case 3? So if fail, okay, let's see if uh, would this work? Clear and then ignore. What does clear do? Clear removes the last, put us back in the normal mode. Because stdc in has a Boolean conversion indicating whether the last input succeeded, it is more idiomatic to write the above as following. Once an extraction has failed, future request for input extraction will silently fail until clear function is called. Thus, after detecting a failed extraction, call and clear is usually the first thing you do. Or they do ignore line twice. Why do they do continue? Oh, I see. To check whether they do a valid input. Let's just define the ignore line separately, I mean. Let's integrate that into our get double. Okay. For fundamental types, our fail extraction due to invalid input will cause the variable to be assigned the value 0. It is fine to call clear even when the extraction hasn't failed. It won't do anything. In cases where we are going to call ignore line regardless of whether we succeeded or failed, you can essentially combine the two cases. So remember whether we had a successful extraction. If success, return success. Okay. Let me type it down. So they're doing CN and stdcn. It's not a function, right? Because I always see it as a function. It is true or false. How do I? Why isn't this going to? How do I go to the definition? Yeah, this is quite confused. So, anyways, Cn is supposed to be true or false, right? So check the current value of Cn, stdcn. And then I think you're supposed to remember it. Yeah. So success Cn ignore. You're going to run these two line anyways. And then if success return success. In end file is a special error that state that means no more data available. This is normally generated after the input operation fails due to no data being available. For example, if you were to read the contents of a file on disk and then try to read in more data after you have already reached the end of the file, and an EOF will be generated to tell you that no more data is available. In case of the file input, there is no problem. You can just close the file and move on. Now consider stdcn. If we extract input from stdcn and there is none by design it would generate an EOF. It will just wait for the user to enter more input. However, cin can generate EOF in certain cases, most commonly when the user enters a special combination for their OS. So it's Control C. Control C and exits the program, right? Windows, both Unix and Windows support entering an EOF character from the keyboard. Okay, let's try this program. enter a decimal. Let's say I do this, enter decimal. Shouldn't it say enter a decimal again? Hold on. I don't need this. And now it says this. I don't know what the issue was. What do they do here? In extracting data to cin, and the user enters an EOF character, the behavior is OS specific. Here's what will typically happen. If the EOF is not the first character of input, all input prior to EOF will be flushed. Wait, what? If EOF is not the first character, all input prior to EOF will be flushed and the EOF character will be ignored. On Windows, any character entered after the EOF are ignored, except for new line. If EOF is the first character entered, the EOF error will be set. The input stream may or may not be disconnected. Although cin clear will clear an EOF error, if the input stream is disconnected, the next input request will generate another EOF error. This is problematic when our input is inside a while loop, as if it gets stuck in an infinite loop of EOF errors. Yeah, let's see. If I do this and then this again, if I do this, why does it say 1 times 1 is 1? Oh, because I'm returning success. And I should be returning X. Wait, yeah. And ender file error is a special error that wait, no, I read that. Since the intent of an keyboard entered EOF is to terminate the input stream, the best thing to do is to detect the EOF and then terminate the program. Because clearing a failed input stream is something we are likely to be checking out for a lot, this is a good candidate for reusable function. Clear fail extraction. If EOF, then exit 0, shut down the program. What does 0 means? 0 mean is it like success? They said Control C enter in Windows, right? So I press Control C enter. Five. Whoops. Let's try that again. Control C and enter. Control C and enter. Is it because of this stdcn that they're asking for another input? Maybe the buffer is empty and they're checking for another input. So let's see what they do. Let's try this. Now they're checking error 4. So what did we learn from error 3? Wait, hold on. What should I write in my note? Zn is a Boolean conversion indicating whether the last input succeeded. I should type this. Uh, when an invalid character is entered, buffer it is left in the buffer. It is left in the buffer. In order to get to cn working properly again, we can use std clear. We can use std clear. Um, let's check the error thingy. Control C, enter. So the program got terminated. It checks the EOF control C in Windows. Extraction succeeds, but the user overflows a numeric value. This is error 4. What happens if a user enters a number that is too large? In the above case, stdcin goes immediately into failure mode, but also assign the closest in-range value to the variable. So in this case, it would be 32767. You can handle this kind of error in the same way as a failed extraction. Okay, so putting it all together, we get this. Let's just copy. Never mind. Then print result course. So you write your program, consider how users will misuse your program, especially around text input. For each point of the text input, consider could the extraction fail? Could the user enter more input than expected? Could the user enter meaningless input, and so on? Input validation is important and useful, but it also tends to make examples more complicated and harder to follow. Accordingly, in the future lesson, we will generally not do any kind of input validation unless it's relevant to something we are trying to teach. So assert and static assert. The Edge browser doesn't take to as long as Opera to open a PDF. In a function that takes parameters, the caller may be able to pass in arguments that are syntactically valid but semantically meaningless. So print division xy static double could not divide by 0. This function does an explicit check to see if y is 0. In the prior lesson, we discussed a couple of ways to deal with such problems, including halting the program or skipping the offending statements. Both of those options are problematic though. If the program skips statements due to an error, then it is essentially failing silently, especially while we are writing and debugging programs. Silent failures are bad because they obscure real problems. Even if we print an error message, that error message may be lost amongst the other program output. And it may be non-obvious where the error message is being generated or how the conditions that triggered the error message occurred. Some functions may be cancelled 10 or hundreds of times. If the program terminates, then we will have lost our call stack and any debugging information that might help us isolate the problem. Abort is a better option for such cases, as typically the developer will be given option to start debugging at the point where the program aborted. I still need to revise the difference between exit, abort, and terminate. In programming, a precondition is any condition that must be true prior to the execution of some section of code. In the prior example, our check that y is not equal to 0 is a precondition that ensures y has a non-zero value before dividing by y. So handle this case. If it is 0, stdc error could not divide by 0. Preconditions for a function are best placed at the top of a function, using an early return to return back to the caller if the precondition isn't met. This is sometimes known as the bouncer pattern, as you bounce out of the function immediately when an error is detected. An invariant is a condition that must be true while some section of code is executing. This is often used with loops where loop body will only execute so long as the invariant is true. Similarly, a post condition is something that must be true after the execution of some section of code. Our function doesn't have any post condition. Okay, wait. So if you have for int I 0 and then I is less than 10, then plus plus I. Invariant is a condition that must be true. This is precondition, invariant, post condition. Yeah, precondition, post condition, invariant. Using a conditional statement to detect an invalid parameter. Uh, Using conditional statement to detect an invalid parameter along with printing an error message and terminating the program is such a common method of detecting problems that C++ provides a shortcut method for doing this. An assertion is an expression that will be true unless there is a bug in the program. If the expression evaluates to true, the assertion statement does nothing. If the condition expression evaluates to false, an error message is displayed and the program is terminated via abort. This error message typically contains the expression that failed as text. Asserts are used to detect errors while developing and debugging. When an assertion evaluates to false, your program is immediately stopped. In C++, runtime assertions are implemented via the assert preprocessor macro, which lives in the cassert header. So cassert for assert, calculate time until object hit, assert gravity is more than 0. Wait, what happens? Assert preprocessor runtime assertions are implemented via assert preprocessor macro. But this is not in a preprocessor. This is not in a macro, I mean. Hold on. Let's see. Initial height. Uh, okay, let's run this. Define assert expression. Where is the assert? I don't understand what this is. In debug. It is -9 in seconds. Why did it process this? Gravity is not more than 0, so how? Although we told you previously to avoid preprocessor macros, asserts are one of the few preprocessor macros that are considered acceptable to use. Making your assert statements more descriptive. Sometimes assert expressions aren't very descriptive. Consider the following statement. If this assertion is triggered, the assert will say assertion failed, found this. What does this even mean? Clearly found was false. But what wasn't found? You would have to go and look. Fortunately, there's a little trick you can use to make your assert statements more descriptive. Simply add a string literal joined by a logical AND. Or if this is false, the entire assert will fail. String literals by default is true, right? So if found is true and this is true, then it's a pass. But there's one thing I don't understand. Does the assertion thing work only in debug mode? So are also sometimes used in document to document cases that were not implemented because they were not needed at the time the programmer wrote the code. That way, if the developer encounters a situation where this case is needed, the code will fail with a useful error message. Oh, so in the error message, it would say, like this found, car could not be found in the database. The assert macro comes with a small performance cost that is incurred each time the assert condition is checked. Furthermore, assert should ideally never be encountered in production code. Consequently, most developers prefer that asserts are only active in debug builds. C++ comes in with a built-in way to turn off asserts in production code. The preprocessor macro is defined. In debug, the preprocessor macro in debug is defined. The assert macro gets disabled. In debug, like no debug, if ndebug is defined, then define this. If the preprocessor in debug is defined, the assert macro gets disabled. Hold on. Oh, it gets disabled. It becomes a void zero. So why isn't this working right now? Maybe I have to do it in debug mode. Most IDEs set and debug by default as part of the project setting for release configuration. Oh, that's why it didn't work. If you're using Visual Studio and want your asserts to trigger in release builds, you will need to remove and debug from this setting. I think I will keep it this way where it only works in debug mode. Why does it say N debug? What is N? For testing purposes, you can enable or disable asserts within a given translation unit. To do so, place one of the following on its own line before any. So N debug means no debug, right? And if no debug is defined, then the assert goes away. I think that makes sense. And if I'm testing, then in a particular translation unit, I can disable assert by using N debug. And this is going to take time. C++ also has another type of assert called static assert. Static assert is an assertion that is checked at compile time rather than runtime, with a failing static assert causing a compile error. Unlike assert, which is declared in C assert header, static assert is a keyword, so no header needs to be included to use it. Static assert condition diagnostic message, and it's checked at compile time. So we can use it with constant, I think, constant expressions. Static assert size of long is equal 8. Size of int is more than greater than 4. Because static assert is evaluated by the compiler, the condition must be a constant expression. Static assert can be placed anywhere in the code file, and static assert is not deactivated in release builds. Assertion and error handling are similar enough that their purposes can be confused. So let's clarify. Assertions are used to detect programming errors during development by documenting assumptions. Or debug error, a bot has been called. Ignore. Okay. So the right way is to do this. Gravity shouldn't be less than 0. Assertions are used to detect programming errors during development by documenting assumptions about things that should never happen. And if they do it, it's the fault of the programmer. Assertions do not allow recovery from errors because asserts are typically compiled out in release builds. You can put a lot of them in without worrying about performance. Error handling is used when we need to gracefully handle cases that could happen in a release build. These may either be recoverable issues or unrecoverable issues where the program has to shut down. Error detection and handling has a both runtime performance cost and a development time cost. In some cases, it's less clear what we should do. Consider a function like this. If x is 0, this function will misbehave. And we need a guard against that. I think you can just use assert. The best answer is both. During debugging, if the function is called when x is 0, that indicates a bug in our code somewhere. And we want to know that immediately. So an assert is definitely appropriate. However, this could also reasonably happen in a VV's build. If the assert is compiled out and we don't have error handling, then this function will return something unexpected and misbehave. So I guess they're doing both then. There are a few pitfalls and limitations to assert. First, the assert itself can be improperly written. If this happens, the assert will either report an error when none exists or fail to report. Second, your assert expressions should have no side effects, as the assert expressions won't be evaluated when debug is defined. And also note that abort function terminates the program immediately without a chance to do any further cleanup. Because of this, assert should be used only in cases where corruption isn't likely to occur if the program terminates unexpectedly. Let me just read this last part and then I will just end the stream. I was expecting to finish chapter 10, but I'm feeling really sleepy. Scope creep occurs when a project's capabilities grow beyond what was originally intended at the start of the project or project phase. Code coverage refers to how much of the source code is executed while testing. Statement coverage refers to the percentage of the statements in a program that may have been exercised by testing routine. Branch coverage refers to the percentage of branches that have been executed by testing routine. And loop coverage means that if you have a loop, you should ensure it works properly when it iterates 0 times, 1 time or 2 times. Okay. Okay. I guess I will end the stream here then. It was a short stream. Short as in I didn't do as much as I expected, but maybe next time I might do more. I want to do more programming instead of just it being a reading stream. Okay, I guess I will end the stream here then.